Deep inside the Himalayas, one river cuts through an almost unreachable landscape. Here, extreme elevation and fractured cliffs turn construction into a survival challenge.
Today, we examine China's staggering concept for an unprecedented Himalayan hydropower system.
The proposal links 5 dams, 4 tunnels, and 5 underground generating stations. Subscribe as we follow this megaproject from first survey to final operation.
During monsoon season, river discharge may approach 14,000 cubic meters per second.
Landslides can bury roads, damage equipment, and isolate crews without warning.
Active faults introduce powerful ground movement beneath massive concrete structures.
Hidden pressurized water can erupt through rock opened by deep tunneling.
Can engineers control this river without underestimating its destructive power?
China's cities and industrial centers require enormous quantities of stable electrical power.
Demand growth increases pressure on generation capacity and long-distance transmission networks. Renewables provide clean energy, but variable output still requires dependable grid balancing. Reservoir hydropower can respond quickly when electricity demand suddenly rises. This river combines exceptional flow with one of Earth's greatest elevation drops.
The engineering target approaches 6 gigawatts, nearly 3 Gorges stations.
Permanent access infrastructure could transform transportation across this isolated mountain region.
The dam requires an entire transportation and utility network before construction begins.
Development must examine sediment, ecosystems, and downstream water consequences.
Success demands electricity, permanent access, and safe control of an extreme river.
Surveying begins from orbit, beyond the reach of conventional ground teams.
LiDAR drones build precise models of cliffs, slopes, and portal locations.
Fixed control points place every road, tunnel, and dam on one coordinate system.
Sonar measures channel geometry, while current meters record seasonal water velocity.
Deep drilling reveals rock strength, fracture direction, and weathered foundation zones.
Each core preserves geological history that surface photographs cannot reveal.
Compression testing determines whether foundation rock can support the dam's enormous load.
Geophones expose hidden weaknesses between widely separated geological boreholes.
Seismic tomography maps faults, voids, and fractured rock inside the mountain.
Multi-year monitoring defines safe construction seasons and extreme operating conditions. The first warning appears where fractured granite crosses the planned tunnel alignment. Those fractures may contain groundwater capable of flooding an advancing tunnel. 4 enormous tunnels must cross 20 kilometers of unstable mountain rock. Hard granite protects some sections, while fault zones create collapse and leakage risks. Surface canals fail because the canyon offers almost no stable construction corridor. A conventional embankment dam requires space, and the narrow gorge cannot provide. Temporary diversion must safely pass extraordinary monsoon flows throughout construction.
Internal heat inside mass concrete can create damaging structural cracks.
Seismic movement must preserve foundation contact and watertight structural integrity. Access corridors need protection from rockfall, avalanches, and moving slopes. Components weighing hundreds of tons cannot use the existing transportation network. Every machine and component requires a carefully engineered transportation chain. Geology, hydraulics, logistics, and concrete behavior continuously influence one another. The final design must control several extreme risks simultaneously. Engineers compare one enormous barrier with a distributed 5-dam cascade. Dividing the elevation drop reduces concentrated pressure at each individual structure. The selected concept uses 5 roller-compacted concrete dams built in coordinated stages. Roller-compacted concrete enables rapid placement using low-heat mixtures and heavy equipment.
4 head-race tunnels shorten the water route and exploit the canyon's elevation.
Underground powerhouses protect critical machinery inside stronger mountain rock.
Water crosses tunnels and penstocks before driving high-capacity Francis turbines.
Deep grout curtains seal fractured rock and reduce dangerous underground seepage. Seismic joints permit movement while preserving continuity and water control.
Temperature sensors and controlled lifts limit heat buildup inside the concrete mass.
Excavated tunnel rock becomes aggregate, reducing imported material and waste transport.
The final design operates as one coordinated hydraulic, structural, and electrical system.
Site preparation begins by anchoring unstable slopes above the access corridor.
Rock bolts and steel mesh prevent loose blocks from reaching workers below.
Excavators carve a permanent service road directly into the canyon wall.
Precision blasting removes targeted rock while limiting damage to surrounding slopes.
A reinforced suspension bridge carries equipment across the otherwise impassable river. Cableways move concrete, tools, and lighter components above unstable terrain. Temporary generation supplies continuous power to tunnels and concrete plants.
Diversion tunnel portals open before the river can be isolated.
Aggregate is separated by size for consistent roller-compacted concrete performance.
Cliff-mounted batching plants reduce hauling distance to each dam placement zone.
Safety teams test warnings, communications, evacuation routes, and refuge chambers.
Heavy construction expands only after access and emergency systems become operational.
High-strength alloy forms each 1,000-megawatt Francis turbine runner. Controlled cooling prevents internal stress from distorting the thick metal casting. Computer-guided machining shapes every blade for efficient, balanced water flow. Laser scanning verifies blade geometry against the hydraulic design model.
Thick steel plates are curved into the turbine's spiral casing sections.
Precision welding creates a pressure shell, distributing water evenly around the turbine.
Subscribe to see every component inspected before reaching the Himalayas. Ultrasonic testing detects internal cracks invisible to ordinary inspection. Precast segments form the permanent lining behind each tunnel boring machine. Load testing confirms each segment resists rock and groundwater pressure. Deep reinforcing ribs help massive spillway gates resist reservoir pressure. Quality inspectors verify hinge alignment before the gate leaves the factory.
Rail carries oversized equipment toward the regional logistics terminal at Lhasa.
Road convoys, cableways, and helicopters complete the difficult final delivery.
Diversion tunnels are completed first, creating an alternate river path.
Reinforced lining protects diversion tunnels from erosion and high-velocity water. Cofferdams isolate construction while preserving controlled river passage.
The river enters diversion tunnels, exposing the first dam foundation.
Crews remove weak material until competent foundation rock becomes fully exposed.
Pressure washing removes particles that could weaken the concrete to rock bond. Drilling begins for the deep grout curtain beneath the future dam.
Pressurized grout fills hidden fractures and forms a continuous seepage barrier. Pressure testing confirms underground flow paths have been successfully sealed. The first RCC layer bonds the dam directly to prepared foundation rock. Bulldozers maintain consistent lift thickness before compaction begins. Vibratory rollers remove voids and develop the required density and strength.
Cooler nighttime placement reduces thermal stress during continuous dam construction.
Cooling tubes remove internal heat before damaging temperature differences develop. Parallel construction keeps the 5-dam Cascade on one coordinated schedule. 4,000-ton machines begin cutting the 20-kilometer headrace tunnels. Rotating disc cutters fracture granite under immense concentrated force. Continuous conveyors remove spoil without interrupting the machine's advance.
Hydraulic equipment installs lining segments immediately behind the cutter head.
Bolted rings and compression seals create a strong, watertight tunnel shell.
Powerhouse caverns are excavated gradually to preserve mountain stability.
Penstock sections are aligned and welded to carry high-pressure water. Sensors suddenly detect rising groundwater pressure ahead of the boring machine.
Water enters through fractures exposed by the advancing cutter head.
Pressurized groundwater breaks through the fractured granite within seconds. Operators stop excavation to prevent further opening of the water-bearing zone.
High-capacity pumps slow flooding while crews withdraw from the tunnel face.
The safety team clears every worker from the affected underground section. If pumping fails, the 4,000-ton machine could remain permanently trapped.
Measured inflow exceeds drainage capacity and threatens the excavation sequence. Engineers trace the breach to a zone missed between earlier boreholes. Cutting remains suspended until the groundwater pathway is mapped and sealed.
Ultrasonic and seismic scans map the hidden channel beyond the cutter head. Pressure data and scans reconstruct the underground fracture network. Angled probe holes reach fractures without reopening the main excavation face. Each probe hole identifies the most active groundwater flow paths.
Engineers prepare rapid-setting chemical cement grout for high-pressure injection. 50-bar injection drives grout deep into connected granite fractures. The mixture creates a continuous underground wall across the connected cracks. The sealed zone cures for 48 hours under continuous pressure monitoring.
Core samples confirm grout completely penetrated the fractured zone.
After successful pressure testing, excavation resumes through reinforced rock.
The first turbine runner enters its completed underground powerhouse.
Laser alignment positions the runner within hundredths of a millimeter.
The generator rotor descends carefully into the stationary electromagnetic stator.
Electrical connections and cooling circuits prepare the machine for sustained operation.
Gas-insulated switchgear controls enormous currents inside a compact protected chamber.
Transformers raise voltage for efficient transmission across thousands of kilometers.
Thousands of sensors measure movement, pressure, temperature, and structural strain.
Foundation galleries reveal seepage changes before they become dangerous. SCADA integrates every gate, turbine, transformer, sensor, and emergency system. Tail race tunnels return water downstream while limiting turbulence and erosion. Electrical tests confirm each generator connection has extremely low resistance.
Rotational laser measurements verify the runner remains centered during movement. The penstock fills slowly while instruments search for leakage or deformation.
Joint seals and drainage systems remain under observation during pressure testing. The turbine runs unloaded while vibration and bearing temperatures stabilize.
Overspeed testing confirms protection systems can control abnormal turbine acceleration.
Emergency controls close guide vanes and safely stop hydraulic power. 900-ton gates verify the reservoir's emergency discharge capacity.
Simulated earthquake data tests alarms, gate logic, and operating limits. Every structural, hydraulic, mechanical, and electrical test meets commissioning requirements. Subscribe as the first intake gate opens for official generation. Reservoir water descends through the completed hydraulic system toward the turbine. The first turbine converts river pressure into controlled rotational energy. Frequency and voltage align before the first unit connects to the grid.
The Cascade delivers power while operators coordinate flow across all 5 stages.
Engineering succeeds here only by understanding the full power of nature.